Hello future pilots, let's start the next chapter of instrumentation, which is the Machmeter. So first we're going to study about high speed flights and the importance of the Machmeter. So let me explain. So when flying at high speeds near the speed of sound, airflow over parts of the aircraft may reach sonic speed, forming shock waves. So let me explain. So the aircraft which are very high speed aircraft which flies near the speed of the sound, airflow over that parts of the aircraft may reach sonic speeds, which is the speed of the sound, and due to this it may cause shock waves. Now what happens in a shock wave, you should know. So in a shock wave, what happens is it increases drag rapidly and decreases the lift, and which causes a nose down pitching moment, which we call is the Mach tuck. All right, and with this makes the aircraft very hard to control. So obviously we have to avoid this because this is very dangerous for the aircraft. So to prevent this dangerous condition, each aircraft has a maximum allowed Mach number. Alright, so we cannot exceed this Mach number because it will cause shock wave, and similarly it will cause a nose down pitching moment and very hard to control the aircraft. We don't want that, right? And this is the reason the Mach meter was introduced, because in this instrument we can see the Mach number and we will know the maximum allowed Mach number which the aircraft cannot exceed, right? So to avoid, so this helps the pilot keeps the aircraft below the limit. So this is the function of the Mach meter and the importance of the Mach meter. Next, we're going to study about speed of sound and its variation. The speed of sound in air changes with temperature. So first I will explain you the relationship between speed of sound and temperature. Warmer air means higher speed of sound and colder air lowers it. So we can say that the speed of sound and the temperature is directly proportional, as warmer air has more speed of sound and colder air has less speed of sound. So we also know the relationship between temperature and altitude, that as altitude increases the temperature decreases. So as temperature decreases the speed of sound also decreases, right? So here it is written temperature decreases with altitude under normal conditions. So the speed of sound generally reduces as the plane climbs higher, right? So now you know that as altitude increases, the speed of sound decreases, because as altitude increases, the temperature also decreases. So with this example, you can confirm it. So at sea level, in standard condition, speed of sound is approximately 661 knots. But at 30,000 feet, it drops to 589 knots. So at sea level, the speed of sound is more because the air is warmer. But whereas at 30,000 feet, we know that the temperature is low. So the speed of sound is also low, 589 knots. Using this formula, you can find out the local speed of sound. This formula states that local speed of sound equals to 38.95 into square root of temperature. So let's find out the local speed of sound at sea level. So we know the temperature of at sea level in standard condition is 15 degrees Celsius. So let's convert it to Kelvin. So it will be 273 plus 15, which makes it 288. So let's put this value into this formula. 38.95 into root 288. You will get 661 knots as it is written here. So now we're going to study how the Mach meters work. So let us look at the construction of Mach meter first. So if you see the construction, you will get to see that there are two capsules. First is airspeed capsule, another one is the altitude capsule. But what is the reason behind having two capsules? I will explain you later. But first let's read this. It uses two capsules, an airspeed capsule that expands or contracts based on dynamic pressure, and an altitude capsule that reacts to changes in static pressure. We already know what the capsule do, right? But what is the purpose or the importance of Mach meter? The importance of Mach meter is to show us the Mach number, because Mach number is very important. Because if we cross the maximum allowed Mach number, it may cause danger to the aircraft. So the importance of Mach meter is to show us the Mach number. But how it shows the Mach number? So Mach number is the ratio of true airspeed by local speed of sound. But where does this Mach meter gets to TAS analysis? So from the airspeed capsule, it gets the true airspeed, and from the altitude capsule, it gets the local speed of sound. How it gets it? So from the altitude capsule, it gets the altitude, right, at which height it is or the altitude it is flying. So from that we know the relationship between altitude and temperature. So from that the altitude capsule gets the temperature, and we also know the formula of local speed of sound, that is local speed of sound equals to 38.95 into square root of temperature. So if we know the temperature, we can also find the local speed of sound. So using this two capsule, the Machmeter shows us the Mach number. Next, we're going to study about the errors of Machmeter. Instrument and position error may affect accuracy with position errors caused by airflow disturbance at the static or pitot sources. So we have already read about instrument and position error, but still instrument error is basically due to manufacturing imperfections, and position error is due to the airflow changes near the static and pitot vents, right? At low Mach numbers, errors are minimum, but at high Mach numbers, errors can increase and sometimes reverse sign. So at lower Mach numbers, the errors are also minimum, but at higher Mach numbers, the error also increase and even sometimes reverse sign, meaning that it can even underread instead of overreading and overread instead of underreading. Most modern aircraft design ensures the Machmeter errors are on the side of overreading to avoid exceeding limits. So in modern aircraft, what happens is that the Machmeter can overread, but it should not underread, because what is the purpose of the Machmeter is the pilot should not exceed the maximum allowed Mach number, right? So it is okay for the Machmeter to overread but not underread. Maneuvering the aircraft can cause unpredictable errors due to airflow changes around the static source. So while maneuvering the aircraft, what it causes is that it changes the airflow near the static sources, which causes an error to the Machmeter. Alright. So now we are going to study that what happens when the pitot or static sources get blocked in Machmeter. So it is similar to what happens in the airspeed indicator, and I've already explained you in that video. So to learn this, there's a trick. If you know put sort, which is if pitot is blocked, it underreads in a descent, that means it overreads in a climb. And if static is blocked, SOD, it overreads in descent, that means it underreads in climb. So if you learn this put sort, you will be able to solve all the questions related to this. And if you want the proper explanation behind this, you can see my video on airspeed indicators. Mach number definitions and corrections. The first one is MMR, which is Machmeter reading. So these are the raw readings from the instrument. Next one is the IMN, which is indicated Mach number. So this indicated Mach number is actually corrected for instrument error. Next one, the last one is the true Mach number, TMN. So this is further corrected for position error. So this gives more accurate Mach readings. So indicated Mach number is corrected for instrument error and true Mach number is corrected for position error. So true Mach number is actually more accurate, and true Mach number reduces the risk of unintentionally exceeding speed limits. So now we are going to study the most important part of the chapter, which is flying at different speeds and altitude. So with this two relation, which is CAS equals to half rho v square and Mach number equals to TAS by LSS, I am going to explain you this three situation. But before that, you should know that CAS is calibrated airspeed equals to half rho v square and v square is true airspeed, and Mach number equals to true airspeed by local speed of sound. Alright, so let's read first. As aircraft climb at a constant calibrated airspeed. So this statement means that we have to keep the calibrated airspeed constant. So let's keep it constant, and you can see that the aircraft is climbing. So what happens in a climb? The density decreases. So if the density decreases, to keep the calibrated airspeed constant, we have to increase the true airspeed, right? And if the true airspeed is increased, in Mach number, what will happen? The Mach number is directly proportional to the true airspeed. So as true airspeed increases, the Mach number will also increase, and the local speed of sound will decrease, right? So here it is written that as aircraft climb at a constant calibrated airspeed, true airspeed and Mach number will increase because of thinning air and temperature reduction. Next statement states that the aircraft is climbing at constant Mach number. So let's keep the Mach number constant. So it is constant. So what happens in a climb? So if we climb, we know the temperature decreases and thus the local speed of sound also decreases. And to keep the Mach number constant, the true airspeed must be decreased, right? So what happens to the calibrated airspeed? Because now we have seen that the true airspeed decreases. So the true airspeed decreases here. And if we are climbing, the density also decreases. So the calibrated airspeed is actually reducing even faster due to the density changes. So here it is written that if climbing at a constant Mach number, true airspeed actually decreases with altitude and calibrated airspeed reduces even faster due to density changes. Next statement states that during descent at a constant Mach number. So let's keep the Mach number constant. So now the Mach number is constant, right? So what happens in a descent? We know in a descent the temperature increases. So as the temperature increases, we have to increase the true airspeed also to keep the Mach number constant. So that now true airspeed is also increased. So what happens to the calibrated airspeed now? So if the as we know that as we go down, the density increases. So density also increases, and here you can see the true airspeed also increases, and thus the calibrated airspeed also increases. So here it is saying that during descent at a constant Mach number, TAS and calibrated airspeed generally increase as altitude and temperature rise. So these relationships are important for managing speed safety in changing atmospheric condition. This is the last part of the chapter, combined Mach and airspeed indicators. Many commercial aircraft combine Mach and airspeed indicators into one instrument for ease of use. So many commercial aircrafts has same in the same instrument, it shows us the Mach number and also the airspeed. So because it is more easy to see, right? This combined instrument may be self-contained or fed by the air data computer. So what do you mean by self-contained? It can be fed by Pitot and static sources, as you can see here, and or it can be also fed by the air data computer. So the airspeed pointer moves over a fixed scale while the Mach number scale moves beneath the pointer. Alright. The ADC based, meaning the air data computer based version, can correct for instrument pin and position errors electronically and uses digital displays for clear reading. So you can see here, this is a combined instrument which is fed by the air data computer. So you can see here it can be easily seen the Mach number, right? So this combined instrument show calibrated airspeed, which is more accurate than the indicated airspeed. So guys, this is the end of the chapter. You can get this notes from the description itself. Thank you for watching.